Thank you very much. And thank you for the invitation. I was very happy to receive it and to be given this possibility to talk about NICER, because many things are going on within the NICER collaboration these days. I will not be able to tell you about everything, and well, you will see in a little while why this is the case, but I will definitely tell you about some super interesting results that we just obtained in the last year. So last year I actually did visit India. I was in Pune for the IPTA conference, and I did give a talk about NICER. And many things happened since then, and I will basically catch a little bit up with the talk from then and also extend it towards our new results that we have. Okay, so why are neutron stars interesting? Neutron stars are interesting because of basically the rule they are exotic kind of objects, which means, in other words, that they have properties which we cannot simulate here on Earth. They have very high magnetic fields. There are different classes of neutron stars, magnetars and pulsars, for instance, just to give you two examples. And magnetars have so far the highest magnetic fields that we know about. As you see in this small animation, a pulsar or a neutron star is a very small star. It has approximately the size of a city. But it has a much higher magnetic field than we have here on Earth. So for instance, just to give you like a numerical example, when here on Earth you have like a magnetic field, depending a little bit upon where you are, but let's say approximately of 0.1 Gauss. And then on a pulsar, you have a magnetic field of 10 to the power of 12 Gauss. And on a magnetar, even 10 to the power of 15 Gauss. So these are not places where we would like to be, because these stars are kind of like very violent from that aspect. But nevertheless, they were found not even 100 years ago. Actually, the very first neutron star that was found was a pulsar, and this detection was made in 1967. So it was not that super long ago, but since then we've learned a lot and we continue learning. So when you read somewhere that neutron stars are exotic objects, it's basically based on their properties, because they are so extreme in terms of physics that we cannot really simulate them here on Earth. Just to give you an introduction. And this is a so-called PP dot diagram. It's actually a short movie of a PP dot diagram. So all these dots are radioactive neutron stars that we have found since the detection of the first neutron star in 1967. So right now we know more than 2,500 neutron stars. And in this group, there are pulsars, magnetars, anomalous X-ray pulsars, all kinds of different neutron star objects. So this should just show you how the periods and the period derivatives, you see the period here and the period derivative here, how they are distributed in such a log-log diagram. So pulsar astronomers, as I am, we work quite a lot with this diagram. And fortunately, the data from this pulsar catalog is updated on a regular basis, so we can actually use it. So each of these dots is a radio kind of like loud neutron star. But shortly, I mean, the very first neutron star, which was a pulsar, was discovered at radio wavelengths. But shortly afterwards, people noticed that there were also neutron stars visible at higher energies. And with higher energies, radio astronomers usually mean everything that is higher in energy than radio. So this could mean not necessarily only gamma rays, but also X-rays, optical pulsars. But you see that radio loud neutron stars are still in the dominant role. And if you wonder what these two distributions are, these are basically two groups of pulsars that we know about. This group here we call the group of recycled pulsars, and this one are normal pulsars. And if anyone has question about that, I'm happy to answer them after the talk. But just to give you like a comparison, that while the first detection had happened at radio wavelengths, we actually expanded the neutron star universe towards all other wavelengths that we can, that we have instruments to measure their emission at. So I'm working primarily with NICER, which is this little box here. It is mounted on the ISS. It is actually an instrument which was built only for the observation of neutron stars that are visible at X-rays. And you see basically, this is a real movie. This is not like an animation or something. You see how NICER is observing neutron stars of different kind while it's mounted on the ISS. And you see like the wings, the solar panels and the wings of the ISS moving through here. So if you wonder if it sometime happens that NICER is pointing in a direction and one of the solar wings gets into the way, yes, this happens quite often, but we know about the others, and so we can kind of like point NICER to a different direction when when a wing is in the way. Okay, now I've been talking about this already. So let's just explain a little bit what NICER is. So NICER is an X-ray instrument. It is sensitive in the range from 0.2 to 12 keV, so kind of like in a soft X-ray range. It has a peak collecting area of 1,900 square centimeters at an energy of 1.5 keV. It was launched actually quite a while ago. If you looked at my very first slide of this talk, you saw that I had written 3 years of operations, because yeah, in June this year we passed the 3 years with NICER since its launch on June 3rd, 2017. And the very first science operations with NICER began basically roughly a month later. And since then we've been getting like tons and tons of data. We have a lot of data, and this data is also public. If anyone is interested, you can definitely have a look at that. And I really like this picture because this is from a time when NICER was still on ground. And I asked one of the technicians once, hey, how big is NICER actually? And someone told me it is as big as a washing machine. And here it looks a little bit bigger than that when you compare this human with this whole box, which is actually NICER. So it's a little bit bigger than that, but let's say roughly like a washing machine. And that's a photo from the launch, which was very successful. And what I would like to talk about now, before I go to the scientific results that we obtained with NICER, I would like to explain to you like how NICER works in a very small nutshell. So basically this whole box here is NICER, and you see like these structures here on the side. So this is actually the heart of NICER. It's called the NICER X-ray Timing Instrument, XTI, and it is basically an array of 52 active silicon drift detectors, which are basically housed in so-called focal plane modules, or FPMs, and each groups of FPMs are actually controlled by something that we refer to as measurement and power unit, or MPU. If you ever analyze NICER data, you will stumble over all of these phrases. So basically, the XTI's concentrator optics are co-aligned, and that way the collecting sky emission, it has like a collecting sky emission from a single approximately free, what was it? I forgot the number now. Yeah, from free arc minutes radius non-imaging field of view. So it's actually, it can actually look at a very small point source like a neutron star, but it also detects emission from its environment. So as I said, NICER is sensitive at X-rays ranging from 0.2 to 12 keV. It has actually a very interesting technique when you are interested in hardware. So it has kind of like two so-called detection chains, as we call it, so that when a photon or any charged particle actually hits the XTI here, the detectors here. So when a photon falls on the XTI silicon drift detectors, it kind of like induces an amplified charge signal. And this signal is then processed by something that we refer to as a slow and a fast processing chain. So actually, this is very unique, this kind of like detector technique, because the slow chain provides a more precise energy measurement, whereas the fast chain provides a higher precision arrival time measurement. So a signal is usually only detected by NICER when a certain threshold in each of these chains is exceeded. Then a kind of like electronic trigger is produced, which basically causes the arrival time and the pulse height amplitude of this incident event to be sampled and digitized. So it can also happen that an event is not strong enough to be detected to basically trigger both chains, but that's okay, because even when only one of these chains is triggered, the event, as we call it, is still being detected. So what makes NICER so good for neutron star observations is that we can actually detect events with our timing precision, which goes into the nanoseconds range. And this is very unique. This usually with previous missions, it was possible to go into the microseconds range regarding the time resolution, which was already great. But when you have a neutron star like a pulsar that really emits its emission very, very regularly, you really want to catch as many of them as you can, because one thing is true when you think about this PP dot diagram with the radio and high energy neutron stars, that there seem to be less neutron stars that are visible at X-rays than at radio wavelengths. And this is certainly also an observational bias that we have, because we first started observing these stars at radio, so we detected more. But another truth is that pulsars, for instance, are not as bright at X-rays as at radio wavelengths, for instance, which means, in other words, you need to observe them longer to collect like more photons from them. Okay, this was a very brief outline of NICER. And yeah, when you look at the comparison of the effective area, you see it's much higher than, for instance, with what we have with XMM Newton. And that's also one of the many reasons, together with the time resolution that we can provide with NICER, why this instrument was basically solidly constructed for the observation of all kinds of neutron stars, including pulsars. Okay, so what happened since NICER's launch and since we started getting data? So these cool diagrams are from the new ADS. So if you are not familiar yet with it, make yourself familiar. It has lots of cool tools how you can visualize different papers. So far we have 65 refereed papers with NICER, and they cover all kinds of topics in these three broad topics here. Most of these papers are led by a science team member, so 57, but as I said, the data is there, the data is free. So we also welcome non-science members to contribute and to analyze NICER data. And so far we published like 70 ATELs. It's really a good and round number, as I noticed just recently. This is a list of all the people who have published NICER data. Most of them are actually science team members, but there are also many who are more active in the radio field, because when you do something like precision timing, as I will come to in a moment, you also need to work closely in collaboration with the radio community. So just to give you an outline how many NICER papers there are after 3 years. So we are really working on a lot of things. So today I would also like to point out the current results of the NICER Precision Timing Working Group. So these are all the members. The chair is Professor Andrea Lohmann. And I also pointed out a couple of other people here whose work I will talk a little bit about today. This is Julia Deneva and Dominic Rowan. So as you see, we have lots of students working on NICER data. So students are always welcome in this collaboration. We encourage to, attend our meetings or to work closely with a science team member in order to learn the analysis, because it's not that hard. It's just probably very different from what you have been doing so far. But if anyone is interested, please let me know. I will forward the word. So the NICER Precision Timing Group is one group in which I'm also active, as you can see. And one of our first papers that was published in 2019 was led by Julia Deneva, and we actually did high precision X-ray timing of 3 millisecond pulsars that we constantly work with within this group with NICER. So why did we do this? Actually, when you have a pulsar here and you are observing its radio emission along its beams, and this radio emission, is traveling through the interstellar medium, which is this cute looking cloud, before it arrives here on Earth. And so we have like an effect on the arrival times at radio wavelengths, at least, like a delay between the higher and the lower part of the radio signal. This is an effect which is called by, which we call dispersion, and it's called by all the electrons that are actually moving in the interstellar medium with which the signal from the pulsar interacts when it travels through the interstellar medium. So when you look at this formula, you see delta T is the delay, this fancy looking D is the dispersion constant. I will not go into detail what this is, but when you Google it, you will definitely find out what kind of term this is. dm stands for dispersion measure, which is a characteristic quantity for each pulsar, and f is the frequency here. So when you compare radio and X-rays, you will notice very easily that due to the higher frequency at X-ray wavelengths, this effect is completely negligible. So this means X-ray data or NICER data is immune to the influence of the interstellar medium. And because this is a fact, we actually wanted to see how precise we can time these 3 millisecond pulsars with NICER data only in comparison with radio data. And here are actually pulse profiles of the 3 pulsars that we have been working with in terms of this study. So all of these are millisecond pulsars. And what you see here are basically pulse profiles with a main pulse and an interpulse. And what you see are actually 2 different curves in each case. You see like a dark curve, like a black curve, and then you see the red curve. And actually the dark curve, the black curve, this is radio data. And the red curve is NICER data. And they are all aligned. So nothing was done wrong with this analysis. They are all aligned. The reason why you see non-alignment between the black and the red curve, and basically all of these three cases is that the X-ray emission of these pulsars is generated in a different part of the magnetosphere than the radio emission. And that's the reason why we have this non-alignment between radio and X-ray data. So these are three pulsars that we study with NICER very, very often. They are so-called legacy objects. And as you notice here, I used, we used actually different energy ranges for each of these pulsars because they're all in different parts of the sky. And for instance, this one here is located in a globular cluster, which means it has a completely different background than, for instance, this body here. So we needed to set up the energy cuts for each pulsar independently. This was necessary. Oh, and if you wonder why in this part, in this lower panel of each of these figures, why there are such wide spaces, well, sometimes when these objects come too near to the sun, we cannot observe them with NICER because the sun emits like lots and lots of photons and other particles. So it is very dangerous for NICER to look very near to the sun at an object. So we have something that we call sun avoidance. And when these objects come too near to the sun, we simply cannot observe them for a little while. Okay, now we have only one pulsar, B1937, because I would encourage you to read the paper for the other results. So basically, these are residual plots. So you have the MJD here on the x-axis and the residual in units of microseconds on the y-axis. And you have like different colored graphs together in one plot. So the NICER residuals are the black parts here, and the other residuals are non-say radio data. So basically, think about the colorful parts are radio data, and the black parts are NICER data. So this is actually a zoom in of this area here, which is great because it shows us much better that with NICER, even when we do high precision timing, we actually obtain much higher error bars than with the radio data. And this radio data was provided, thankfully, by the Nanograph collaboration with who we are working like very, very closely with. And we are aware that we have like these much higher error bars than the radio data, but that's not really the point here. The point here is to create a data set, basically a timing study of these pulsars without the influences of the ISM, because of the interstellar medium, because when we compare the results of the X-ray timing with the results of the radio timing, we might actually also help to find out how much, for instance, red noise we see in this data. So this project is a close collaboration with the radio community because we really want to understand how clean the residuals are that we actually do see here. Okay, one other paper that we published since I was in India last year was actually led by one student, Dominic Rowan. He did an excellent job together with his group of other students in looking at profile evolution for 3 X-ray emitting millisecond pulsars, actually the same objects with which we worked previously for the NICER timing study. So he used a much larger sample of data. He used actually 2 years of NICER data. And here you have pulse profiles of B1937, B1821, J0218. And when you look from top to bottom, all of these energy ranges are different. So he basically took the whole NICER data and looked at different energy ranges when he built these profiles. So why did he do this? Well, we actually wanted to know if we can see profile evolution with X-ray data and X-ray data only. So basically, profile evolution stands for frequency. Basically, when you look in the radio data at different frequencies, when you look at the same pulsar and use different frequencies, and when you have profile evolution in this data set, then you can actually see that with each different frequency range, a pulse can be moving in phase. And we wanted to know if we do see something like that also in the NICER data, which is the reason we took 2 full years of NICER data for this examination. And here you have in this purple accounts the light curve, and we fitted each of these peaks with Gaussian and also with a Lorentzian fit to actually get like all these slopes together. And we did this for each of these pulsars. And then we wanted to know if the separation between main pulse and an interpulse is changing, and what the full width at half maximum is of each of these components. And we basically did this for all 3 pulsars again. So here you have the full width at half maximum, here you have the energy, and here you have the pulse separation in cycles. And these are 2 different pulsars. So we actually did this examination for all of them, and also for the other one, for J0218. And actually we found that in the case of this pulsar, the separation between its 2 pulsars, the main and the interpulse, actually decreases when you go higher up in energy. And we could determine this with higher than 3 sigma confidence. So this is actually a very interesting result. What we also did was to look at phased resolved spectra. So here, for instance, you have B1937, and you have pulse 1 and pulse 2, which means main pulse and interpulse. And we basically used different fitting methods and also looked at different energy ranges. So this was basically to improve the already existing models that are already out there with up-to-date values for the power law fits. And we could actually reproduce the already existing results very, very easily with this 2-year data set, which was actually great because it showed us, okay, we can connect with NICER to this kind of emission physics that we are addressing with NICER. Because as I said, when you think back about the profiles with the NICER timing study, you saw like the black and the red curves. So you saw that there's like a non-alignment, and I said that both kinds of emission, radio and X-rays, they are not being generated at the same spot within the pulsar magnetosphere. This is definitely the case. We can see this in the data, but we also want to find out where in the magnetosphere is this X-ray emission being generated. And that's also one big background question behind this paper. So this is the last spectrum. We have more in the paper, but I would encourage you to read the paper. So basically the results of the study were that we could update the previously existing model parameters with a single absorbed power law model. We did not find any evidence of additional blackbody emission component in the case of the first 2 millisecond pulsars, B1937 and B1821. We found an additional component in J0218 at energies below 1 keV, at which it is very difficult for NICER to make like reliable measurements. And then what we also saw, what I did not mention at all previously, I apologize, was that in the case of B1937, when you look at the main pulse and the interpulse, and the main pulse is P1 here, and the interpulse is P2, that these 2 peaks have different photon indices, which suggests that they are being generated also at different parts of the magnetosphere. And that's interesting because after all of these years, we still don't really have an answer how pulsar is working in terms of its multi-wavelength emission. Okay, so these were the results of the NICER timing working group. Now I would really like to switch to something which has been probably in your ears for quite some time already. So the reason why NICER was built, one of the many reasons, was to be able to determine the equation of state in the case of neutron stars, and with that determine the mass and the radius. So the NICER light curve modeling group is doing exactly that. We have lots of different working groups and the collaboration, and we definitely have more than I can talk about now today. But the results of this working group produced in the last couple of months are very, very interesting. So I wanted to include you in this adventure on how to determine the radius and the mass of a neutron star. So basically what this group is using to determine the mass-radius relation is something that we refer to as pulse profile modeling, which is a technique with which basically probes the general relativistic effects which are happening on a surface of a neutron star. So basically you see two different neutron stars here, and you see something that we refer to as hotspot here and here. And here you have the light curves. So let's play this. Whoop. Let's play this again. And you see when you have like the influence of strong gravity and therefore relativistic effects, that the light curve here is very much different when you have the scenario of no gravity, which is a special scenario because this is not how nature actually works. So, but these guys are measuring are actually the light curves of these hotspots, and they try to reproduce them with a variety of codes and try to understand basically how these hotspots are built up to generate these light curves. So just to give you like an idea about all of the effects that are coming into the game here, which are kind of like really complicated. So you have like local radiation beaming, you have ray propagation, you have bending of light, you have gravitational redshift, you have rotational metric deformation, you have lots of quadrupole moments and higher order multipole moments. So this is really, really complicated work. And I just noticed because last year I was pretty curious, and I asked them why it's taking so long to make this comparison. Not that I was kind of like not patient enough, but we all wanted to know how the results looked like. And they explained all of these intricacies to me, which I now understand make it actually very, very hard. So imagine when a star spins, I don't know why it's doing that. Then the flux in the spectrum of the X-ray emission, and the X-ray emission is coming from these hotspots. When you look at it as a distant observer, this X-ray emission is kind of like modulated in a periodic way, because you have this kind of like light curve, or you have like a pulse profile when you are observing a pulsar. So basically, when you map the surface emission into such a pulse profile, you can only do this when you have like relativistic ray tracing through space-time of a very rapidly rotating star. So when you have the model of the surface emission, like of the surface here of this hotspot, you can actually calculate the expected pulse profile for a given exterior space-time solution, when you know with which instrument you are making these observations. And that's what we are doing also with NICER. So what these guys are doing is actually they're coupling the these light curve models with something that they call statistical sampling software, and they use Bayesian inference to derive like posterior probability distributions for these space-time parameters from which they derive the mass and the equatorial radius. So all what they need is actually pulse profile data. But to get like a very good result, solid result, they have kind of like they have a lot of constraints. So for instance, they need pulsar that is spinning very rapidly, like with a frequency of more than 100 hertz. And they also need like very high quality phase and energy resolved pulse profiles, which means, in other words, with a time resolution of less than 10 microseconds. And they need a lot of photons. And that's where NICER is coming into the game, because due to its higher collecting area, it's actually collecting lots of more photons from these stars. So the required number of photons is approximately 10 to the power of 6. So the brightest millisecond pulsars that we are observing with NICER, we need a little bit over 1 megasecond to achieve that goal. And that's the reason why we are also doing this with NICER. So these hot regions on our millisecond pulsar, as you see here and here, are actually we think, caused by magnetospheric currents and the energy that is actually stored in them, basically in the surface layers of the star. So we don't know exactly yet how this is working, but we definitely can reproduce pulse profiles from a pulsar by analyzing these hotspots. And last December was finally the month in which all of these papers came out. So one of the first papers was this one, led by Sławko Bogdanow, who's the leader of the light curve modeling group. Basically in this paper, they showed us the whole millisecond pulsar X-ray data set that they were working with. And I will only show you excerpts of this pulsar, J0030, because, well, you will see why. So what they did in this paper is to time it, to do long-term timing. You have, again, here, residuals in this plot, and this is like only X-ray data this time. They looked at the profiles. This is a NICER profile in a certain energy range. And this is the an XMM Newton profile. And you can actually see that we do collect more counts per bin. This is why NICER is more sensitive for these kinds of studies. Oh yeah, what I wanted to say, sorry about this. These gray areas, they actually use them for the spectral analysis, which is on the next slide. So you see the spectrum here, and there are actually two spectra, two graphs in this plot, a red one and a black one. And one of them is from the main pulse, and the other one is from the interpulse. So in this community, people usually say pulse 1 or pulse 2, P1 or P2, whereas radio people usually say main pulse and interpulse, which is funny because you mean the same thing. But yeah, there are kind of like different ways to name things. So this pulsar, I'm showing it to you because it was studied extensively with by the NICER collaboration. It was detected to be a radio pulsar initially. It has kind of like a spin frequency of 205 hertz approximately, but then just a couple of months later, it was also discovered to be an X-ray pulsar. And it is actually one of the brighter millisecond pulses at X-rays, which is also the reason why NICER is studying it. So why this is a spectrum. You see kind of like a different diagram here. This is what we call a two-dimensional histogram of NICER XTI counts versus pulse phase and photon energy here. So these are basically the counts that we detect with NICER put into this very colorful graph. So these are all the characteristics that they studied in this paper, not only of this pulsar, but they also used a couple of others that are all in the paper, but since these they produced all of these plots for each of them, I think one of them is really enough here. So what they also found out with this study is basically that the spectrum of this pulsar from these individual peaks, main pulse and interpulse, can be very well described by a single temperature hydrogen atmosphere spectrum. So the purpose of this whole paper was to show that this data set and the other data sets that they analyzed were actually useful for the search for the mass and radius of the corresponding pulsars. And then in the second paper, which arrived, I believe, even at the same time, they actually described how they determine the emission from the hotspots on a very rapidly rotating neutron star. So this is a more theoretical paper, but it is really, really interesting if you want to know how they are doing this. This technique has been in the community for quite a while. It's not new, but what was missing apparently so far was data with enough statistics provided by an instrument like NICER, and that's the reason why we're actually doing this. So in this paper, and it's really long, so I will not go super much into detail here. They basically describe, when you look at this neutron star here, this is a sketch of a neutron star. It shows basically the geometry of a hotspot on the neutron star surface, because these hotspots are on the surface. And the neutron star is rotating with an angular frequency omega, which I believe you see here. So the photon is being emitted, or a photon is being emitted from the surface at angle alpha, and with respect to a local surface normal, which we call n, and this one is here. And it's basically seen in a local static frame. But the moment it's being sent off, it is deflected by a total angle, which is this one. And without going too much into detail regarding that, they discuss all of these effects in this paper, and they apply different simulations to the observations that we have with NICER. These simulations are summarized here. They use the Schwarzschild-Doppler approximations. They also use the oblate-like Schwarzschild approximations, and they compare all of them against each other. So, and they find a very good output between all of their codes, especially when they compare them with numerical calculations, which is actually a strong suit of these models. So if you want to know, if you are interested in theory and want to know how they are doing this, this is definitely the paper to read. So why have I been talking about all of this? That's an interesting question. So basically I wanted to come to this paper, which was the paper that reported like the first determined like mass and equatorial radius of a neutron star. And it took all of the results from the previous two papers into it and basically used them. So this paper by Riley et al. Has the very first results for exactly that same millisecond pulsar, J0030, that we discussed already previously. So this is actually a phase-folded diagram. You have something that high energy people refer to as light curve. Radio astronomers would say phase diagram here, and then you have again these XTI counts here in this very colorful plot. So basically the top panel is a pulse profile, which was summed over many channels, and in the bottom panel you have basically the phase channel resolved count numbers for the same subset. What they also did during the study is actually shown here. They checked the temperature distribution of these hotspots. And one reason why these simulations took such a long time and are actually computationally very expensive is to find out what the temperature distribution of these hotspots is. So basically in this figure here, this is a scenario. All of these diagrams are for a model with a single temperature region. Basically, this hotspot here has only one temperature, and that's what the ST is standing for, single temperature. And they simulated this for the northern rotational hemisphere of the star and for the southern rotational hemisphere of the star. What they also did was they made the same checks with a model that had like concentric single temperature regions, and you see them here. And this is definitely more complex, and when you are into numerics, you can immediately see why these calculations take definitely more time than these ones here. I mean, it depends also on lots of other characteristics, but this is one reason why this is so complicated. And then they also looked at more complicated temperature distribution. So basically, you have a hotspot with an outer region that has a different temperature than the inner region. And when you wonder what these parts are, this is basically the same hotspot at the other hemisphere, at the southern one. And of course, nature is usually kind of complicated. So what we would like to work is actually this scenario. But this study showed very well that this is not working like that. The results of this paper pointed at actually this more complex scenario where you have like a more complex temperature distribution in each of these hotspots, which of course is computationally hard to determine, but this is what the data in the end showed. With data, I mean observationally and also theoretically, numerically. So the big summary of this paper is that they used the Bayesian parameter estimation for the mass and the equatorial radius, and they came up with these two numbers, which is actually great. We have been waiting for these values for quite some time. This study also opened up, of course, as usual, more questions. In particular, because it showed that the models with hotspots in the same hemisphere are actually pretty much favored by the current models. But if you have hotspots in the same hemisphere, you need more parameters to describe them, which actually tells us the models that we currently have are not precise enough yet for this kind of calculation. What the study also showed was that models with kind of like simply connected, like single temperature hotspots are pretty much disfavored. And yeah, this is what I was talking about when I said a moment ago, nature is not working this way. Nature is way more intricate in these terms. So if you're interested, please look at these papers. We definitely have more of them, but I wanted to point especially this study out to you because I really, before I understood how they were determining these temperature distributions, I kind of could not get my head around why it takes so much time computationally. But if you have all of these relativistic effects coming into the game, it is really not easy. And what this paper showed us, what these results overall show us, is that we have way more work to do to basically place the generation of the X-ray, of the soft X-ray emission that we observe into one area in the magnetosphere of the star where it's generated. So of course, we also want to know the mass and radius of a neutron star in order to solve the equation of state. But on the other hand, we also want to know how these stars are generating their emission. And I think actually all of the nicer studies that we have carried out are pointing in one sense or the other at this question. So I have no idea if I rushed through this or not, but I'm happy to take questions. So let me just summarize. NICER has been in operation since 2017, pretty much, June. And we took operations, we began with science operations, not debugging operations, but real science operations just shortly after. There are lots and lots of interesting science projects going on that have been published already, and there's way more going on within the working groups. So the NICER Precision Timing Group, just to give you an example, has so far published like 1 year of timing results and 2 years of X-ray pulsar data to search for profile evolution, which we actually have found in one of the, statistically significantly in one of the free pulsars that we studied. And the NICER light curve modeling group is super active in determining like the mass and radii of different neutron stars. So I only showed you the example like for one pulsar, but they have at least 3 more objects that they are working with. And it's really an active research environment. So yeah, thank you so much for your attention. I'm sorry if I rushed through some things. So if you have questions about a specific slide, please let me know.
Thank you so much, Natalia. Very nice talk, and for bringing this incredible astrophysics and astronomy effort to our doorstep. It's really amazing to see how the effort that goes in, and you kind of summarize everything very nicely. So I'm just going to read out you're welcome, the questions from the chat. The first one is actually from a YouTube. So how does one cope with the background noise that comes along with these signals? How do we effectively study these signals?
Very good question. This was my first question to the deputy PI before I joined the collaboration. How are you doing this? So let me go. Let me just go back to our nice looking pulse profile. Okay. So what I do study within the collaboration are actually these 2 pulsars here. And what I look for is a correlation between its radio giant pulse emission and its soft X-ray emission. And of course, at X-rays, because you have this detector in space, it does not only catch photons from the source, it also catches lots of other things. So our background emission rate in terms of photon count rates is much higher than actually the count rate of these objects. But the trick is, and I really say trick because I mean it this way, is when you study these objects, you basically don't study like the whole light curve or the whole phase diagram here, but you reduce your area of interest, let's say in phase, to just a specific area, because with this you lower the background. So what I mean with this is, when I want to look for a correlation between radio and X-ray data, and I have this data set, I would basically reduce my analysis to only look at photons in this phase range, for instance, or this one, and would not look at the whole light curve, because then the background would be huge. But when I reduce my analysis to a certain phase range only, I actually decrease the background significantly. And this is the way I can do what I'm doing within the NICER collaboration.
Okay, thank you. The next question is, a lot of photons should be emitted from high altitude rather than from the surface hotspot. How to determine the emission height if having considered this effect? So hopefully you can see it. I'm not quite sure I understand the question, but maybe you can interpret it better.
That's okay. So I don't have all of the numerics in my head right now that they are applying, but I definitely know that they are using something that we call filtering. So they are excluding like lots of events for the reduction of this data, same as we do in the case of these millisecond pulsars, because the detector gets hit by lots of different things. In this case, it's more coming from cosmic rays or other parts of space, not necessarily from the pulsar. So in the case of these hotspots, when you really look at just some small areas on the surface of the star, I assume that they compare like their numerical simulations with the observations and kind of like retrace this emission, but I don't have like any specifics about this in terms of numerics. I'm sorry.
That's fine. Are these details in some paper that maybe the person who asked will look it up? Okay.
They are pretty much, and I'm certain, all in this paper here, this one, which is actually pretty long, and it really tells you how they are extracting the information they need to.
Thanks. The next question, I gather that 2 groups studied the data independently and came up with a best fit 2 spot, and the other came up with a best fit 3 spot model, but they kind of agreed on the radius constraints. Are there more groups conducting further studies on this data? And is there more data on the same object being collected still?
Yes, so we have so-called legacy objects sources within the NICER collaboration, which means they have been in the NICER proposal from the very beginning. So the timing working group, these 3 objects that I actually showed are the legacy objects for the timing working group. For the light curve working group, basically this object and also like 3 other MSPs, millisecond pulsars, are constantly being observed. So we are not finished yet. And yes, there is one big group in Amsterdam, and they are working with us. Anna Watts is leading this group, and she's also a NICER member. And then there's, I think, one more group either somewhere in the United States or in Toronto, but the NICER light curve working group and that group, they're working together, so they're communicating between each other.
Okay, thank you.
So they're not competing, they're actually working together.
Mm-hmm. The next question is, neutron stars are highly dense objects, denser than a nucleus in parts. And in the nucleus, the nuclear transitions emit gamma rays. So how come it emits X-rays?
I think this picture is a very simplified one. I think the fact that we have all kinds of neutron stars that do not only emit their emission in one wavelength range just tells us that our current models, like in the case of pulsars, you have the polar gap, slot gap, and outer gap model. They are just simplifications. This is not how it's at least not in its core, how it's working, because all of these emissions, when you look at different pulse profiles, and for instance, like in the case of the Crab pulsar, which we also observe with NICER, you see an alignment between its radio profile emission components and its high energy emission components. This actually says that, that all of this emission is generated like in the same spots in the magnetosphere. But the moment you have like you have like high time resolution observations and look at single radio photons or high energy photons, you notice that this is not the case, not necessarily. So it's way more complex than just, assuming that that a neutron star emits only radio emission or gamma ray emission and nothing else. So what we know is that while the radio emission is classically assumed to develop along these two emission beams, the high energy emission is being generated farther out in the magnetosphere, so farther away from the pulsar. And we think that the one emission model for gamma ray emission or high energy emission in general is our reconnection events for which occur near the last closed magnetic field line, something that theorists call the Y point because of the process of reconnection. But I could not name you like a theory and say, hey, this is why we see X-ray emission in the end, because we don't understand enough yet.
The next question is, how does one extract information possibly from this data about the composition of neutron stars? So going beyond mass radius, how would you get some compositional information?
Oh, I don't know. I have not worked with that. I'm sorry.
Okay. The next question, again from YouTube, the live stream, is how big of a spectral library is needed to study emissions? Sounds like a pretty broad question, but again, I will leave you to interpret it.
In general, yeah. So I would say whatever you can get. I mean, the only, when you look at the whole electromagnetic spectrum, the only piece that is currently missing is basically in the infrared wavelength range. And IMA, the Atacama Large Millimeter Array, has been able to close this gap to some extent, but not completely. So when I study a pulsar, I really look at all of the wavelength ranges possible and where I can find data. Optical wavelengths are a bit troublesome because the brightest optical pulsar is actually the Crab pulsar, and there are like only 14 to 16 pulsars roughly that can be observed at optical wavelengths. And when I say observe, I really mean with these big telescopes like the BLT in Chile, so with the bigger telescopes. We don't know yet why we have not detected that many pulsars at optical wavelengths, but not that many seem to emit that kind of emission. The Crab, for instance, is one that does, because its emission is observed throughout like almost the entire electromagnetic spectrum, and that's the reason why we are studying it a lot.
Okay.
I would say, just to conclude on that, sorry, I would say all the emission at which with which the star emits at different wavelengths, and this is just wishful thinking, but ideally, if the data were taken simultaneously, this would be somehow like the best data set. But I know that's hard because we have different instruments. Some of them are in space, some of them are on ground. So as far as I know, we have never had like a data set of a pulsar taken at all wavelength ranges simultaneously, unfortunately.
Okay.
Sorry, I interrupted you.
No, not at all. Okay. So that's about it for the questions. I don't see any other questions popping up, and it's exactly the hour. So thank you very much again, Natalia, and look forward to more.